Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay. And also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. And also guys, please share my details with your friends so that they will also be able to watch my free live lectures and will be benefited by it. Okay. Okay guys, so let's get started. So this is the ninth part of the series of CSIR Net Physics 2021 paper solution. Okay, so question, I'm going to start with question. Okay, first question of this series is, it's a good question guys. The nuclei the nuclei the nuclei of 137 CS cesium, okay, 137 CS decay by the emission of by the emission of decay the emission of the emission of beta particles with half-life of with a half-life with a half-life of with a half-life of 30 30.08 years 30.08 years. The activity the activity the activity that is in units of disintegration per second disintegration disintegration per second disintegration per second, or we can say becquerel. Okay, becquerel, or in short we can write BQ of a BQ of a 1 milligram 1 milligram 1 milligram source of 1 milligram source of 137 cesium. Okay, 137 cesium. 137 cesium CS. Okay, prepared on prepared on January 1st, 1980, as measured on January measured on January 1, 2021 is closest to. Okay, and options are: option A is 1.79 into 10 to the power 16. Option B is 1.79 into 10 to the power 9. Option C is 1.24 into 10 to the power 16, and option D is 1.24 into 10 to the power 9. Okay, so this is the question, guys. A very good question, guys, and it will clear your concept. Okay, I'll read the question for you. I'll explain the question and then I'll solve it. Okay, so question is: the nuclei of 137 CS. Okay, so we have 137. We have a nuclei of 137 CS. Okay, that cesium decays by the emission of beta particle. Okay, so beta particle emits emits from this nuclei. Okay, and with half life of 30.08 years. Okay, so this nuclei of cesium 137 has a half life that is given 30.08. Okay, 08 years. The activity, we need to find out activity in the units of disintegration per second, or becquerel. Okay, so we need to find the activity in units of disintegration per second. Okay, of 1 milligram source of 137 CS. Okay, so we have to find out activity, and we have source. We have 1 milligram of cesium 137 cesium. Okay, which is prepared on January 1, 1980. Okay, so this is prepared on January 1980, and half life of it is given, that is 30.08 years, right? As measured on January, which is prepared on January 1st, 1980, as measured on January. So when we measured on January 2021 is closest to. Okay, so we need to find out activity, okay, of 1 milligram source of 137 CS, which is prepared on January 1, 1980. Okay, and as measured on January, and which is measured on January 1, 2021 is closest to. Okay, so okay, it's a good question, so I'll explain now. So we have a formula for activity, that is A equal to lambda n. So this is the activity formula, guys, you need to note down. I have explained it in my nuclear physics class. Okay, the detailed course of nuclear physics I have completed in 2 lectures of total time duration of 4 hours and 30 minutes. Okay, so I would request you watch that. So there are 2 classes of nuclear physics, and in these 2 classes nuclear physics is completed, and each classes is of more than 2 hours. Okay, so watch that class. I have explained everything in detail. Okay, so A equal to lambda n. Okay, so this is the activity, and this is going to be A equal to lambda n naught e to the power lambda t, because we know the value of n is, this is a formula which I have already explained, n equal to n naught e to the power minus lambda t. This one, n equal to n naught e to the power minus lambda t. Okay, So now this is going to be lambda and not e to the power minus lambda d. Okay. So now you need to understand, guys, this one time. So we have half-life given, guys. Half-life of this cesium 137 is given. We have given T half. T half is given, that is 30.08. 30.08. Okay. So this is we have been given 38 years. And so from here we can find the lambda, because we have T half. We have lambda equal to, because we know lambda equal to 0.693 upon T half. T half is 30.08 years. Okay, so we've got the T half, that is lambda value. Okay, and N0, we need to find N0, guys. This is equation number 1. We can say N0. N0 is, we have been given this one. This is very important, guys. Okay, so for this one, the activity, okay, of 1 milligram source of 137 CS. So 1 milligram source of 137 CS. 1 milligram means this one. So N0 is going to be 1 milligram means 10 to the power minus 3 gram. Okay, upon, because we need to find number of nuclei in 1 milligram of 137 CS. Okay, so this is going to be that 10 to the power 3 gram into 3 gram upon 137, because 137 CS, right? This one, because atomic mass is 137 of cesium, into Avogadro number. Okay, Avogadro number we know 0.02 into 10 to the power minus 23, right? So this value, this is the value, guys. Okay, so we have N0 value, we have lambda value. We'll put in equation 1 for getting activity. So activity is going to be this is lambda value we'll put is this is, right? So this is going to be 0.693 upon 30.08 years. 30.08 years. Okay, into this one N0 value, this one, because we have 1 gram of cesium 137, right? So it means the N0 number of nuclei is going to be 1 gram upon the atomic mass of cesium into Avogadro number. Okay, this is very important. You need to note down this one. Here you can write N0 equal to that mass into Avogadro number upon atomic mass. Atomic mass. Yeah. Atomic mass, right? This you need to know. So now very simple calculation. So this is going to be N0 value 10 to the power minus 3 upon 137 into 6.02 into 10 to the power 23. This one 10 to the power 23, not minus 23, guys. My apology. Okay, so this is 10 to the power 23 and into e to the power minus lambda t, right? E to the power minus lambda. Lambda value we know this value. 0.693 upon 30.08 into T. T value, guys, here, T value. So you need to understand this. Okay, we need to find out the activity, okay, of 1 milligram source of cesium 137 prepared on January as measured on January 21. Okay, so this time duration is going to be that T is going to be, because since prepared means prepared on 1st Jan 1981, right? 1981, and measured on 1980, not 81, right? Okay, 80. Measured on 1st Jan 2021, 2021, right? 2021. So the time is going to be, this implies t value is going to be this minus this, so this is going to be 40 years. If you subtract this from this, okay, so measured minus prepared, right? So this is 40, this is years, okay. So if you solve it, a simple calculation, if you solve it, this you need to note down, okay. So if we solve it, then value of a is going to be 0. You can solve it by calculator, okay. 0.0393 0.0393 into 10 to the power 18, and this is disintegration per year, guys, because time is in year, right? Disintegration per year. This is disintegration per year. Now we need to find disintegration per second, okay, important thing. So this is going to be, right, A equal to disintegration per second we need to find. So this is 0. 0.03 0.0393 into 10 to the power 93 into 10 to the power 18 upon, we need to convert it into, it's a disintegration per year, right? So we need to convert it into disintegration per second, means we'll divide by 365 into 24 into because in year there are 365 days, in hour there are 24 hours, and then in hour there are 60 minutes, and then in 60 minutes there are 60 seconds, okay. You'll solve it, and this value is going to, and this is the disintegration per second. The DPS we can write in short, or Becquerel, disintegration per second. So this value A is going to be, if you solve it, so this you can calculate it, okay. So this is going to be 1.24 into 10 to the power 9, disintegration per second, okay. So this is the answer, guys. Very good question, very conceptual question, okay, formula based question, okay. So which option is matching, guys? 1.24 into 10 to the power 9, disintegration per second. This one, option C is matching. So option C is the correct option, right? Okay. Wait, option C. No, option D, guys. My apologies. Option D, because this is 10 to the power 6. Okay. So this is the answer, guys. At 1.24 into 10 to the power 9. So option number D is the correct option. Okay. I hope, guys, you have understood it. Next question we are going to do. It's also a good question, guys. Next question is, okay, so this is This question is to measure the height. Very good question, guys. I'm solving part C questions, guys. Okay, part B are completed. So this is the ninth part of this series of CSIR Net Physics 2021 paper solution. Okay, so to measure the height, to measure the height, to measure the height, to measure the height h, height h of a height h of a column of liquid, column of liquid, column of liquid helium, column of liquid helium, column of liquid helium in a container, in a container, in a container a constant current, a constant current I, constant current I is sent through, is sent through, is sent through an NBTI wire of length L, of length L, as shown in the figure, as shown in the figure. I'll make a figure. Okay, I'll draw the figure as shown in the figure, as shown in the figure, in the figure. The normal state resistance, the normal state resistance, normal state the normal state resistance, normal state resistance, normal state resistance, normal state resistance of the NBTI wire, of the NBTI wire is R. Okay, so normal the normal state resistance. Okay, the normal state, the normal state resistance of NBTI wire is R. Okay, if the superconducting, if the superconducting if the superconducting transition temperature, superconducting transition temperature of NBTI wire, of NBTI is almost equal to is almost equal to 10 Kelvin, 10 Kelvin, then the measured voltage, then the measured voltage then the measured voltage, V, measured voltage V, which is function of H, is best described by the expression options are given. Option A is IR, the current, R is the resistance, okay, of normal state. 1/2 minus 2H upon L. Option B is IR 1 minus H upon L. Option C is IR into 1/2 minus H upon L. And option D is IR 1 minus 2H upon L. Okay, so these are the options, guys. Okay, I'll make a figure and then I will explain the question. After that I will solve it. Okay, so this is going to be, the figure is shown and this is like this. So this is the liquid. This height is H, and this height is also H, guys. So total height is 2H. Okay, because in the figure it is clearly seen. Okay, and then there is a wire. This is the wire. Okay, wire, and then this is connected with voltage V. Okay, so this is the figure given, guys. Okay, this is the figure. Now I will explain the question. Okay, so to measure the height H of a column of helium liquid. Okay, to measure the height H of column of liquid helium. Okay, so this is the liquid helium. This is liquid helium, and we need to find the column, the height of column liquid helium, means this height. Okay, H. Okay, helium in a container. Okay, to measure the height H of a column of liquid helium in container, which is in container. Okay, it is shown which is in container. Okay, a constant current I is set through an NBR wire. Okay, so this is the NBR wire, and constant current we have set. Constant current is set through it, this wire. Okay, so this is the wire. Next, wire of length L as shown in the figure. Okay, so this is the wire, and its length is L, guys. So length from here to here, this is L length. Okay, very important. Now, as shown in the figure. Okay, so the normal state resistance of NBI wire. So for NBI wire, the normal state resistance, when the NBI wire in normal state, its resistance is given, that is R. Okay, if the superconducting transition temperature, of NBTI and the NBTI wire, the superconducting transition temperature of NBTI wire is given, that is almost equal to 10 Kelvin, then the measured voltage, we need to find measured voltage, which is function of H. Okay, measured voltage VH is best described by which option? Okay, this is the question. Okay, and this is the figure. So I'll solve now. Very good question, guys. Okay, so I'll write the statement here. Okay, this you need to understand. We have given a superconducting critical temperature. Okay, for this this one. Okay, so NBIT the wire is given, that is 10 Kelvin. Okay, so since superconducting critical temperature, since superconducting critical temperature for NBTI wire is given. Okay, NBTI wire is given, that is almost equal to 10 Kelvin, that is given. Okay, and the partition of the wire, and the, or we can write the part of the wire. Okay, or the partition of the wire, the partition, or I'll write part. Okay, the part of the wire, immersed in the liquid helium, immersed in the liquid helium, in the superconducting state, helium is in the superconducting state with zero resistance, with zero resistance Okay, the part of the immersed part of the immersed part of the wire, this is part of the wire immersed in the liquid helium is in superconducting state with zero resistance. Okay, so this part of the wire which is immersed in helium is in superconducting state. Okay, it is in superconducting state. If it is in superconducting state means the resistance is zero, right? This we know. So superconducting state with zero resistance, while the part above the liquid, the part above the liquid, is in normal state, okay, with is in normal state with resistance R. Okay, this one very important because here we have been given in the question, right? This one where NBTI. Okay, so as shown in the figure, the normal state resistance of NBTI is R, and if the conducting transition temperature of the NBTI is this. Okay, so here you can see because to measure the height of H of a column of liquid helium, right? So here you can see this is liquid helium, and this part of the wire is in immersed in the liquid helium, means this is in superconducting state. Okay, so superconducting state means so you can see superconducting state means the resistance is going to be zero, and above this part, right, this is in normal state. This wire is in normal state, right, because it is not immersed in liquid helium. Okay, so now we have a formula, guys. Okay, I'll show you. We have a formula. We know resistance R equal to delta L upon A, right? Delta L is constant. Delta that delta is constant, or we can say resistivity, right? So R is delta R equal to delta L upon A. L is the length of wire, is the area of the wire, right? Cross-sectional area of the wire. This we know. We have already studied this part, right? Okay, so from here, what we can do, that the resistance of the wire of length L. Okay, now we'll find, because now you can see you need to understand this. It is in liquid helium, means this is in superconducting state. Okay, and this is a normal state. Okay, and now you need to understand this, that the resistance of this part of the wire is zero because it is in superconducting state, but this part is not zero. This side is H and this side is H. Okay, so now we can write the resistance of the wire of length L, right? So now we'll find resistance of wire, resistance of the wire, resistance of the wire of length L, of resistance of the wire of length L. Length L is, that is R dash. Okay, R dash we need to find. This is R, guys. Okay, this is R. This one is R. So this we can write this one. delta, so this is going to be L minus 2H L minus 2H upon A, right? This is the length. This is the length, okay? L minus 2H upon A, right? This one. Okay. So now this is the one, right? So L minus, so this is for the resistance, okay? That part of the resistance of the wire, okay? Because below the liquid, that the resistance is 0, okay? This one, that is the R. And also we can write this R dash equal to, we can write L delta L minus 2H, okay, upon A. We can divide by L and multiply by L, okay? So then this R dash is going to be delta L upon A into L minus 2H, right? And delta L minus A is resistance, right? This is equation number 2. So this value is this, okay? So this one, this is the R, okay? Resistance, or this is R, okay? This is for total length R, or for remaining part the resistance is going to be this, okay? Now this part is R, so this is R dash is going to be R into L minus 2H, right? R into L minus 2H. L is also there, guys. Here L is also there, right? So upon L. So we can, what we can do, this is L minus, this is L, okay? So we can write R dash value equal to R dash value, okay? R we can take common, and this is L by L is 1 minus, and this is 2H upon L, 2H upon L, okay? So this is R dash, guys. R dash value, R into 1 minus 2H upon L, 2H upon L. Now we need to, now we know, since we need to find V equal to IR, right? V equal to IR, or in this case IR dash, right? Current is I given in the question, okay? I current close. So so we can put the value. So V is going to be, so V is going to be IR, means this one, I into R value is this, R into 1 minus 2H upon L, okay? So V value is going to be IR, this one, this is the IR into 1 minus 2H upon L. This is the answer, guys. So which option is matching? Option D is matching. Let's see. IR into 1 minus 2H upon L, okay? This is the answer. This is the answer. IR 1 minus 2H upon L. I hope, guys, you have understood it. Next question we are going to do, guys, we are going to solve, okay? This is question number, question number 2. Question number 3 we are going to solve. Question number 3 is, this is also good question, guys, okay? So I'll solve this question by two method, okay? Okay. Question is, the dispersion relation, the dispersion relation, the dispersion relation, dispersion relation, dispersion relation of a gas, of a gas, dispersion relation of a gas of non-interacting bosons, of non-interacting gas of non-interacting bosons, bosons in dimension, in d dimension, in d dimension, in d dimensions, okay, is given, that is E, which is function of k equal to a k to the power s, okay, where a and s are positive, where a and s are positive, are positive constants, positive constants, okay, the boson Einstein condensation will occur, okay, the Bose-Einstein, my apologies, Bose-Einstein, Bose-Einstein Bose-Einstein condensation Bose-Einstein condensation Bose-Einstein condensation will occur for will occur for will occur will occur will occur for all values of for all values of for all values of number A, D greater than S, number B, D plus 2, D plus 2 greater than S. So S is between D plus 2 and D minus 2. Okay. And now option C is S greater equal to 2 independent of D. 2 independent of D. Okay. And option D is S greater equal to D greater equal to 2, D greater equal to 2 independent of S. Independent of S. Okay, so this is the question, and I'm going to solve this question by two methods. Okay, so first I will explain the question. Question is the dispersion relation of a gas of non-interacting bosons. So there is a gas of bosons, and those bosons are non-interactive, okay, in d dimensions, and that gas is in d dimensions, okay, and the dispersion relation of a gas of non-interacting bosons in d dimensions is given, okay, is given I can write here is, okay, d dimensions is ek equal to a k to the power s, okay, k means E is a function of k, that is energy is given a k to the power s, where a and s are positive constants, okay. Bose-Einstein condensation will occur for all values of, okay, so these are the options. So So we have to tell the condition for Bose-Einstein condensation. Okay. So for which condition out of these four is the correct for Bose-Einstein condensation to occur? Okay. So this is the question. So now first method I'm going to solve with first method. First method is this one. First method is, so we have been given dispersion relation. Okay, so we have been given dispersion relation, that is Ek is given equal to A k to the power s, A k to the power s. Okay, so this is Ek given. Okay, and so now what we can do is we can study different cases. Okay, so first case is for non-relativistic system. Okay, for non-relativistic system in 3D. Okay, for non-relativistic system, for non-relativistic system in 3D. For non-relativistic system in 3D. Okay, so for non-relativistic system in 3D, we know E is going to be equal to P square upon 2m. Why P square to 2m? Because potential energy is 0, because particles are, or bosons are, non-interactive. Okay, so this is going to be h cut square k square, P value we know h cut k, right, upon 2m. Okay, so from here, since the P equal to h cut k, okay, P is momentum. So from here we can write the and value of E we have been given. So A k to the power s equal to h cut square k square upon 2m, right? And this h cut square upon 2m is constant, and this is also constant. So we can write these are constant, right? So from here we can write these are constant, and k to the power s equal to k to the power 2 means s value is 2. Okay, s value is 2, and we are talking about 3D since d value is 3D, right? 3. It from this we can say d is greater than s, right? Because s value is 2. Now second case is second is similarly in relativistic case. So this is for non-relativistic system. Okay, now for relativistic case. Okay, this is for non-relativistic system in 3D. Okay, now for relativistic case in 3D. Okay, for relativistic case in 3D. Relativistic case in 3D means for this one relativistic for relativistic system in 3D. Okay, so this is going to be now for relativistic system in 3D. We know the formula, guys. This E equal to PC. Here E equal to P square upon 2m, right? So for relativistic case, this is equal to PC, because V is 0, because particles are non-interacting. Okay, PC. So E value we have given, right? E value is given. So E value we can write. E value is given. E value is given. This is E value is A k to the power s, right? A k to the power s, and P value we know h cut k c. Kc are is constant, A is constant, right? And k is means k to the power s equal to k. That implies value of s equal to 1. So from here, and since it is in 3D and d is 3, right? It implies E is greater or equal to s. Okay. Case third we can study for 2D relativistic for 2D. In 2D relativistic case, 2D. In 2D relativistic case, 2D relativistic case, again this is 2D relativistic case means again this E equal to PC, E equal to PC, and here P is value of P is root Px square plus Py square. Okay, so then P is going to be EC. EC means again H cut K. Sorry, this equal to H cut K, right? So E is going to be PC means E is PC, right? So E value is going to be a k to the power s, that is going to be a k to the power s, right? A k to the power s. This is going to be h cut c k, right? Again k to the power s equal to k, that implies these are constant, right? A and h cut c are constant, so s equal to k. Sorry, s equal to 1. So that implies this is in d equal to 2d means d equal to 2 dimension, right? So this means d is greater than s. So in all cases you can see d is greater than s, right? So d is greater than s, this is the answer, guys. So which option is matching? Option A, d is greater than s. In this way we can solve it. Now the second method is just a simple method. Okay, second method. Second method. Okay, so this is for this formula based. Okay, for B condensation, Bose-Einstein condensation. For Bose-Einstein condensation, we have this formula d upon s minus 1, that is greater equal, that should be greater than 0, guys. So this is important, this formula is note down. Okay, so both Bose-Einstein condensation, this one, d upon s minus 1 should be greater than 0. So that means d upon s greater than 1, or we can write d greater than s. This is the answer. Okay, so this is simple one, you need to note down and memorize it, guys. For Bose-Einstein condensation, d upon s minus 1 should be greater than 0. D upon s minus 1 should be greater than 0. Okay, so d upon s minus 1 should be greater than 0. So from here we can write d upon s greater than 1 and d is greater than s, right? I hope, guys, you have understood it. Simple simple thing. Okay, so this is the one. Next question, guys, question number 4. This is also a good question. Question number 4 is, a perfectly a perfectly conducting fluid. So perfectly conducting fluid means this is perfectly conducting. Okay, perfectly conducting fluid perfectly conducting fluid of permittivity of permittivity of permittivity of permittivity epsilon and permeability and permeability 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 and permeability mu flows with permeability mu flows with a uniform velocity with a uniform velocity with a uniform velocity uniform velocity v in presence of in the 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 presence of time dependent time dependent time dependent electric and magnetic field time dependent electric and magnetic field respectively if there is a finite current density in the fluid. Okay, if there is a there is a there is a finite current density there is a finite current density in the fluid in the fluid in the fluid then options are option A is del cross V cross B P cross B that is equal to del B upon del T del B upon del T. Okay, del B upon del T, and option B is del cross V cross B equal to minus del B upon del T minus del B upon del T. Option C is del cross V cross B equal to root epsilon mu del E over del T Okay, and option D is del cross V cross B equal to root minus root epsilon mu del E upon del T. Okay, so this is the question, guys. A very good question, and I'm going to explain it first. Okay. So question is a perfectly conducting fluid. So we are talking about the fluid which is perfectly conducting, okay, of permeability given epsilon and permeability mu, flows with a uniform velocity, okay, that flows with a uniform velocity v in the presence of time dependent electric field and magnetic field, okay, respectively, E and B respectively, okay. If there is a finite current density in fluid there is a finite current density, okay. Okay, then we need to find which option is the correct. Very good question, guys, and I'm going to solve it. Okay, so okay, so guys, first we'll write generalized Ohm's law for conducting fluid. Okay, so the generalized Ohm's law, the generalized Ohm's law for conducting fluid. This formula you need to note down. Okay, generalized Ohm's law for conducting fluid, conducting fluid is given by J equal to sigma E. This we know, right? As like J equal to sigma E we know, but generalized Ohm's law for conducting fluid, that is sigma E, that is sigma is the this is sigma density, right? Surface density. So sigma E current density, okay, the surface density. Okay, so sigma E plus sigma V cross B. Okay, this you need to note down, guys. If fluid is conducting and flowing, okay, with velocity v, and with in the presence of electric field and magnetic field, in that case this current density, that is J, is equal to sigma E plus sigma V cross B. Sigma E plus sigma V cross B. This is important formula, guys, you need to note down. Okay, so J equal to sigma E plus sigma V cross B. Okay, so sigma is surface density, right? Okay, now this is the formula. Now what we can do is, if there is no net current, okay, so if there is no net current in conducting fluid, okay, so suppose, so we can say if there is no net current, if there is no net current, okay, it means that implies J equal to 0, because if there is no net current means then current density, that current density J is going to be 0, value of J is 0. Okay, thus above equation becomes, and then we can write our equation because J equal to 0, right? So this is the case if there is no net current, okay, in the fluid. There is no net current in the fluid means there is no net current, that means J is 0. Okay, okay, so in that case this equation will become, this is 0, right? 0 equal to sigma E, this formula is important, guys, okay, into sigma V cross B. Okay, this one. So we can write, because sigma we can go in right hand side, so we can write implies E plus V cross B equal to 0 we can write. Okay, and now guys, we have a formula, that is, since curl of E equal to this formula, Maxwell's formula, curl of E, that is equal to minus del V upon del T. Okay, so curl of E equal to minus del V upon del V upon del T. So in place, so what we can do, we can take curl on both sides. Okay, first we will take curl on both sides. So this equation is going to be curl of del cross E plus curl of V cross B, right? So equal to 0. Now since del cross E equal to minus del V upon del T, so in this equation we can write this is minus del V over del T. In place of this we have written, okay, so in place of del cross E we have written minus del V upon del T plus curl of V cross B, that is equal to 0. Okay, so from here we can write curl of V cross B, curl of V cross B. Okay, curl of V cross B, that is going to be equal to, this will come here, that is del V upon del D. This is the answer, guys. So which option is matching? Okay, so which option is matching, guys? Option A is matching. Option A is one. Curl of delta V cross B. Curl of V cross B. Curl of V cross B. Curl of V cross B equal to del V upon del T. Del V upon del T. Okay, so this is the answer, guys. I hope, guys, you have understood it. Okay, guys. So before wrapping up the class, I would request the student that first I would like to inform you, the student, that guys, please check my playlist. Okay, many courses have been completed, guys. So many detailed complete courses have been completed. So I would request you, please check my playlist and watch all the detailed courses, right? And that courses are going to help you to crack the especially the CSIR NET exam, and then and this is also going to help you for GATE, NTA, PSD, SET exam, TIFR, Jest, Jest, IIT-Jam, etc. Okay, and also, guys, please, guys who have not subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, and also, guys, I would request you, please share my lecture details with your friends so that they will also be able to watch my free lectures and will be benefited from it. Okay, and for checking, so I would suggest you guys, I would request you, please watch my playlist, guys. In playlist you will get all the courses, all the detailed courses. Okay, okay, guys, so thank you so much. Bye now.